We are continuing to talk about rational functions. We've had a whole entire lesson on finding horizontal asymptotes. We've had a whole entire lesson on solving inequalities. And that was a nice one to kind of get you used to the fact that we can't have 0 in the denominator, because what you're going to learn today is a 0 in the denominator, any value that makes that happen, that means there's either a hole in the graph or a vertical asymptote. Those are both called points of discontinuity. That's a fancy way of saying it. So I just want you to recall that a rational function is just a polynomial over a polynomial. It's almost like a function divided by a function. Since we're dividing, we're going to have restrictions on our domain. And that's a fancy way of saying there are some x values that we don't want to plug in. We can't divide by 0. We talked about that in our last lesson. So we have to consider any x values where the denominator is equal to 0 and restrict them from the domain. And where that happens, you're either going to have a vertical asymptote or a hole. Vertical asymptotes and holes occur when the denominator is equal to 0. How can we distinguish between the two? So here you just have, like I said, there's not going to be a lot for you to write. I just want you to look at this and listen. A hole occurs when you have a factor that's going to cancel out. So if you see the factor on the top and that same factor on the bottom and they cancel each other out, that's where you have a hole. Sometimes. And a vertical asymptote is going to occur when you have a factor in the denominator that's not going to cancel out with something on the top. So you might have heard me say a little bit under my breath there, that rule for holes is almost always true. We're going to talk about the cases today where you can't, that's not true, okay? Let's just look at holes really quickly. Here are a couple of equations, a couple of functions that have holes, and I just want you to notice what that looks like. Once everything is factored, you can see that like for this f of x function, that x minus 1 would cancel with the x minus 1 in the denominator. That doesn't mean there's a hole at -1. You still have to think forward and know that I'm really setting that equal to 0 and solving. So there's a hole at +1, at the x value +1. The hardest part of today for some of you is going to be figuring out there's a hole at 1 what? Okay, that's the pre-calc component of this. In algebra 2, you just learn, oh, there's a hole at 1. Cool. And then g of x, you can see the same thing. If you were to write all of these out, you have an x minus 1, an x minus 1, and x minus 1 on top. On the bottom, you have an x minus 1 and an x minus 1. So all of the denominators would cancel out, and if you're a person that wants to see that, you can just write it right down here. That's our g of x, which doesn't go with this graph or anything, but I just want to show you that the x minus 1s cancel. There's a hole at 1. Here is what a hole would look like in a graph setting. You can see it right there. It's kind of teeny tiny. Unfortunately, your graphing calculator won't show you in that way. I need to show you on the graphing calculator how you can find a hole in a table of values. So we're going to look at that today. But in this graph that's pictured, you can see there's a hole right there. It says the graph above has a hole at 1. And here's the pre-calc component. It's going to be a little bit challenging for some of you. Look at how you write limit statements for holes. Okay, I'm going to zoom in. I'm going to say this out loud a couple of times so you can be really comfortable with it. This says the limit as x approaches 1 from the left. From the left. That's what that negative up there is. It doesn't say the limit as x approaches -1. Don't say the limit as x approaches 1 negative. It's the limit as x approaches 1 from the left side. Well, as x gets closer and closer to 1 on the left side, y gets closer to 3. Now, luckily, that goes with this graph. So if you want to look at the graph with me, here's what that means. I'm going to draw some arrows. As the graph approaches the value of 1, the x value of 1 from the left, that y value is, watch my pen, that y value is getting closer and closer and closer to 3. Okay? As x approaches the value of 1 from the right, the y value is approaching 3. And look at what the limit statement says. Look at how that's set up so that you can get used to writing those and reading them. So the limit as x approaches 1 from the left, that's approaching the y value of 3. The limit as x approaches 1 from the right, the y value is approaching 3. Yes. You're not always going to have a graph. You might just be given limit statements and you might have to know, oh, there's a hole at 1, 3. You can get that from here. There's a hole at 1. And as the x value is approaching 1 from the left and right side, the y value is getting closer to 3. Okay. Let's wait and see what kind of stuff we're going to have on the back of the notes, okay? So, I just kind of we're just introducing you to the idea here. Now, vertical asymptotes, here's a couple of situations of functions that have a vertical asymptote. I want you to notice, like f of x, nothing cancels. And so what I have left down here in the denominator is that x minus 1. That didn't cancel out with anything on the top. That means we have a vertical asymptote at 1. And then g of x, the same thing happens, because I really want you to notice what happens on g of x. Okay, I'm going to expand this out, just like I did over there with the whole. X minus 1, x plus 2 is on the top. And x minus 1 shows up twice in the denominator. And you might think, well, then there's going to be a hole based on what she just told us a second ago. There's a hole at 1. Well, here's that exception to the rule. You can't, look what I'm pointing to, you can't have a hole on a vertical asymptote. So if this situation comes up where, yeah, some stuff cancels at 1, but you still have left over in the denominator x minus 1, that means that there's a vertical asymptote at 1, which means there is no hole. So vertical asymptotes kind of trump holes. Does that make sense? There's no way you could say that this graph has a hole on this vertical asymptote because the graph isn't ever even going to touch that. Yes. Okay, if I just canceled out a couple of x plus 3's, then the graph would have a hole at -3 and a vertical asymptote at 1. But this is a special case, okay, and it's going to drive some of you crazy, where you might just jump to the conclusion, oh, there's going to be a hole at 1, and then you're going to write, and there's a vertical asymptote at 1, and you're going to have to pause and think, wait a second, there can't be both happening there. So cross out the hole if there's just a vertical asymptote. And here's kind of a picture of a graph that has a vertical asymptote at 1. And then look at your limit statements. Look at the difference between, over here when you had a hole, your output was a number. Over here, when we're talking about vertical asymptotes, the equal to part is going to be some infinity symbols. Negative, negative, positive, 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 negative, negative, positive, something like that. But you're going to have infinity symbols when you're talking about vertical asymptotes. So you might just be given limit statements, and you might be asked, does this have a hole at 1 or a vertical asymptote at 1? Well, it's a vertical asymptote because the graph is getting infinitely larger or smaller at that x value. And the graph, look what it's doing. As it approaches the vertical asymptote from the left, y's are getting smaller, negative infinity. As it approaches that vertical asymptote from the right, the y's are getting larger. You're increasing without bound. All right, turn to the back. We're going to start off pretty gentle here. Example 1. Determine where we have any holes or vertical asymptotes. So look at A. Does anything cancel out? Okay. The x plus 3's would cancel. That means this rational function will have a hole at x equals what? -3. Is there anything left in the denominator that did not cancel? Okay. Then that means like just with our sign charts, we would say we would never, ever, ever want to plug in a 5 because it would create a 0 in the denominator. But because that didn't cancel with anything in the numerator, we say that this graph has a vertical asymptote at 5, at the x value of 5. In just a minute, we'll be able to tell a little bit more. We're going to push ourselves to think critically, and where would that whole, what order of pair would we get? So let's keep going. Look at B. Is anything going to cancel out? Okay. What? Okay. It might help if you expand out. I'm just going to be creative in the way that I do that. So I've got a couple of x minus 2's on the top, and I got a couple of x plus 1's on the bottom. It looks like what's going to happen here is x plus 1, you could only cancel 1 on the top with 1 on the bottom, but just start crossing through all of them that match. So I might think at first glance that this is going to have a hole at negative 1. Why is it not going to have a hole at negative 1? Yeah, because you're going to have a vertical asymptote at negative 1, and you can't have a hole on a vertical asymptote. Now, is there anything else that's going to cancel? X minus 2, a pair of those. So this will have a hole at 2. But it's not going to have a hole at negative 1 because, in this particular case, it has a vertical asymptote at negative 1, at negative 1. And you would never have the same value here as you have here. You're never going to say, like, there's a hole at 3 and a vertical asymptote at 3. That doesn't make sense. Okay? The only difference that C has going for it is that the denominator is not factored yet. So take a second and factor the denominator. Is anything going to cancel? This graph does not have a hole. What would I never, ever, ever want to plug in on the bottom? 0. So we're taking that factor, we're setting it equal to 0, and we're saying, okay, then that's going to be a vertical asymptote at x equals 0. Now, you guys are really smart. Look at this right here. What are we going to do with that? It's not a difference of squares, though. It's a sum of squares, but that's not really anything that's helpful because you can't factor it. So do we need to set that equal to 0 and solve? Try it on your paper. Set that equal to 0 and solve and see what happens. You're going to get an imaginary, oh no. All that means is you can plug anything you want here. You can plug in anything you want because you're going to square it and add 4. Is there any danger of that information ever being equal to 0? That's never going to happen. It's mathematically impossible for us to plug in anything and square it and add 4 and get 0 from that. So just ignore that. That's not going to affect this rational function. So the only thing that happened on C is there's a vertical asymptote at x equals 0, which is essentially just the y-axis. Okay, let's step it up a notch. And we're going to write limit statements. So now we're kind of finally getting to the pre-calc component of this stuff. But look at your directions really closely. It says write a left and right limit statement as x approaches 2. So specifically, on the next 3 examples, our limits will all say as x approaches 2 from the left and 2 from the right. Because the directions say on all of these, write a limit statement as x approaches 2. So let's go ahead and get all of the limit statements set up. The limit as x approaches 2 from the left. Don't put negative 2. Put 2 and then put a negative symbol as a superscript of f of x. And then the limit as x approaches 2 from the positive direction, 2 from the right. of f of x. And go ahead and do that on B and C. I'm only doing this because the directions told me to. So read on your homework because it's probably not going to be 2 again. So let me just recall with you on the first page. What we learned is if there's a hole, then our limit statements will have a numeric value after the equal sign. If there is a vertical asymptote, our statements will have some kind of infinity symbol after the equal sign. So what we first need to do is look at A and see if there are holes or asymptotes at 2. Well, the 2 isn't going to cancel out with anything at the top. So what does that mean is happening on the graph at x equals 2? There's a vertical asymptote at x equals 2. I'm making a little note to myself. So that means I'm either going to have some positive infinities, negative infinities, some kind of infinity happening. Now, how in the world do I know if the graph is going down or up as it approaches this? So we're going to make a sign chart. And put 2. Now, we used to just all willy-nilly, we would just pick a value to the left and a value to the right and we'd call it good. But you need to understand, because we're talking about limits, we need to pick something really close to 2 on either side of 2 to see what's really happening to the graph. Okay? So I really just kind of want you to think of 1.9 and 2.1. It doesn't get very tedious, so watch. 1.9. If I plug in 1.9 up here, I'm going to end up with a positive times a positive over a, what's 1.9 take away 2? That's a negative. So it still works the same way as it used to, but you need to pick values really close to that number. Don't pick 0 and 3. Alright, so we end up with a negative. So pause. Guess what we just learned? As the graph gets really, really, really close to 2 from the left side, the graph approaches negative infinity. It decreases without that as we approach 2 from the left. So try to visualize that right now. Close your eyes. There's a vertical asymptote of 2, and the left part of the graph is going down forever as it approaches that. Okay? Now let's do the sign chart, and let's pick 2.1. 2.1 minus 1 is still positive. We're going to get a positive there. And then 2.1 take away 2 is still positive. And so we get a positive. And what we just learned is, when we're really close, when we're just on the other side of 2, on the positive side of 2, our graph is increasing without that. It's getting bigger and bigger and bigger. So sign charts are really the only way for you to tell if you are increasing or decreasing without that. Now luckily on B, we're not going to have to do that, and here's why. Does this graph have a hole or a vertical asymptote at 2? It's got a hole. How do you know? Those would cancel. Good. So hole at x equals 2. Okay, now that we know that it's a hole, remember, we don't have to do a sign chart because these aren't going to be infinities. These are going to be some kind of numeric value. Well, check this out. All you have to do is you have to pretend that those cancel out and now plug in that 2. What's 2 plus 4? 6. And what's 2 take away 3? Negative 1. And what's 6 over negative 1? Then that's what value you put there. There is, but the directions just say to worry about as x approaches 2. So yes, it's good that you notice there is a vertical asymptote at 3, but because of the directions in front of us, we don't need to worry about that. It doesn't say write all the limit statements. It just says as x is approaching 2. Yes. Mm-hmm. Mm-hmm. You don't really have to sit there and do that over again because technically we're pretending that cancels out. That's still going to be 6 over negative 1, so those will always match each other. So you don't have to do a sign chart for a hole. We do need to do a sign chart to see if the crack is going up or down near a vertical asymptote. So where would the hole be located here? What's the ordered pair? At 2, -6, you would see a hole on the graph. Not on your graphing calculator. I'm going to show you what that looks like in just a second. Okay, let's look at C. What's going on at 2 in this problem? There's a vertical asymptote. Well, I thought they were going to cancel out, and that would mean there's a hole. There's still going to be, once a pair of these cancels out, there's still going to be an x minus 2 in the denominator. Good, that means there's a vertical asymptote at 2. You can't have both a hole and a vertical asymptote in the same location. So if that happens, vertical asymptotes trump holes. Okay, now that we know that, darn it, we're going to have to make a sign chart because we're going to have some infinity stuff happening here. So let's do that. Sign chart. It is, but again, yeah. I know, and I did the same thing. And I was like, I feel like we're leaving a whole bunch of stuff out here, but it's because of the directions. I just having this look at the value. Okay. See if you can do this now. See if you can pick 1.9 and 2.1 and plug them in and do your sign chart and get your infinity symbol situated. It doesn't really matter. You can go ahead and just plug into everything that's in front of you. That's a good question. 1.9. That's always going to be positive. So it's the limit statements that really make you think. Now are you glad you're going to have 2 days to practice this stuff? Yeah. Okay. Do you have any questions about that before we move on? I want you to get your calculator in front of you and we're going to see what this stuff looks like on the table. Yes? No. That's a great question. You're totally allowed to get positive, or negative, negative. A rational graph can be, remember we've seen all kinds of crazy rational graphs. They can both be going up towards the vertical asymptote. Like, I'm going to draw a little micro picture here, but you can have a graph going up, like that. That'd be positive infinity as we approach that vertical asymptote. So there is no rule that says these have to be one or the other, or like opposites of each other. All right, so I want to show you, let's type A into the calculator and then hit Control T, and let's see what the table says. You guys really do this with me. I think this has a lot of value in showing you how useful your calculator can be in some situations. Home 1, no 2. Open a new graph document. Home 1, no 2. Something that you found? Okay, I will. Control divide. Control divide. Type it in just like it is on the paper. When you get what's on my screen, I want you to stop right there. Hit tab and arrow up and make sure that you type in just like this. X minus 1, x plus 3, x minus 2. Annabelle, did you get it? All right, you guys, listen. This is a really strange situation. Look at the graph. You can't see all of it, so I want you to do the whole zoom fit thing. Do zoom fit. You should know exactly how to do that. Menu, window zoom, zoom fit. It zoomed way out. Okay? Now, you can clearly see with your eyeballs that this has a vertical asymptote at 2. Yes? Okay? You can clearly see with your eyeballs that as it gets closer to that vertical asymptote from the left, it's going towards negative infinity, the y values. And as it approaches that vertical asymptote from the right, the y values are getting infinitely larger, which aligns with how we did it all mathematically. All right, so it's great to see that. But I want you to hit Control T, and I want to make sure you know how it's going to look in the table. What does it say at x equals 2? Control T will pull up a table. It says undefined. That's the calculator's way of telling you x is never going to be 2. There's something going on at 2. Now visually, we can tell, luckily, that that's a vertical asymptote. Just wanted to show you that. Now here's what I want you to do. Hit Control T again to hide the table. Hit Tab, arrow up, and I want you to delete that one, Control Delete, and I want you to type in what's on the paper for B. I need to show you how to notice that there's a hole in the graph on the calculator. And we know that B has a hole because we did it on the paper. So x minus 2, x plus 4, over x minus 2, x minus 3. Now it's still on zoom fit, which is totally fine. That doesn't really matter at all. But just kind of as a thing, I want you to notice here, and Annabelle had brought this up, this does have a vertical asymptote at 3. We can see that. On the paper, we discovered that there's a hole at 2, negative 6. You are not able to see that on the graph. You're not going to have a big open circle there. So here's the only way you're going to know that there's a hole or something funky going on. Hit Control T. There's something funky going on at 2 and at 3. Well, we know there's a vertical asymptote at 3 because on the paper we can tell that, and on this picture we can tell that. So there's not a vertical asymptote at 2, so my intuition says there's probably a hole there, but I want to be more detailed with you. So is everybody here? We're going to change the table settings to see what happens as x gets closer and closer to 2 from each side. So here's what I want you to do. Menu, table, edit table settings. And since we're interested in what's going on near 2, let's start at like 1.98 and let's have the calculator count by 0.01, by hundredths. And then hit OK. So start just on the left of 2, count by hundredths. And look, this is really cool for you to see now. On the paper, you said we're getting closer and closer to negative 6, and now the calculator justifies that for you. You can see that as we're getting closer and closer to 2 from the left or from the right, we're getting closer to negative 6 in the y values. I show you these things so that if you are weak here, maybe you can be strong here. Or if the calculator thing is just really not helpful to you, then you can be really strong here. But either way, you need to know more than one way to approach it. Okay? So I just wanted to show you that. We are going to, you can put your calculator aside, we're going to skip example 3 and come back to it because it's the most intense of the day. And we're going to go to 4. I think these are kind of fun because I'm a nerd, and you are going to have a test question like this. Test. She's telling us what a free response test question is going to be. It's going to be the similar skill set right here, where I tell you some features and you have to sketch it. Or maybe you have to mathematically find the features and then sketch it. So let's see what's going on here. It says f of x has a hole at 1. As x approaches 4 from the left, y's increase without bound, and as x approaches 4 from the right, y's decrease without bound. What are these last two statements telling me? That there's a what? There's a vertical asymptote at where? At 4. That's where I would choose to start. This is a very rough sketch. There will be a little piece of gridded graph paper for you on the test. But that means I'm just going to go ahead and say, all right, 1, 2, 3, 4. There's a vertical asymptote. Now, I'm not told anything about a horizontal asymptote, because that's not in today's lesson. You might have that on your test. But we don't have to worry about that. We've got these last two statements that say, as we approach 4 from the left, y's increase without bound. And I'm using pencil for a specific reason. Now, again, there's nothing saying that the x-axis is the horizontal asymptote. You could, like, dip down here if you wanted to or something. But I don't know why I just kind of stick with that. Okay. Now, as x approaches 4 from the right, the y values decrease without bound. Now, let's address the fact that we have a hole at 1. All I'm going to need to do is take my eraser and just erase a little section of the graph and put an open point there. That's it. That's the only information we're given, so that's the best we can do. Those really aren't too terrible. You can do B. Do B. Also. And Addison, here's a good example of when we would have negative infinity in our limit statements. And you're learning you can have more than one hole. You just can't ever have a hole on a vertical asymptote. Any questions about those? Those are kind of gentle and hoping. Now we're going to go. That's fine as long as it on graph paper where you have your -2 or wherever you've drawn your graph, that there's a hole right underneath or above, depending on how you draw it, and the line lines with that -2. I mean, I guess I could, you wouldn't be able to, with just this information, you wouldn't be able to tell me the order of characters. But if I gave you the function, and you had to find all of the things, you would at that point be able to tell me what the character is. We're going to practice that way. Okay? So look at example 3. This is probably the most challenging part of today's lesson. That doesn't mean give up, it means pay extra close attention. So it says write an equation. So we are given limit statements. We're going backwards. We're given limit statements and we have to write a function. And at first glance, these really aren't that bad, but the devil's in the details. So look at A. I'm noticing there's a limit statement for as x gets closer and closer to 3, y's get closer and closer to 5. Is that a hole or a vertical asymptote? It's a hole, and where is the hole? There's a hole at 3, 5. Because these limit statements are about as x gets closer up to 1 on the left and right, we're approaching the infinity step. That's a vertical asymptote at where? 1. So I want you to go ahead and get yourself set up to write this function. Get f of x equals and draw a fraction product. There's a hole at 3 and a vertical asymptote at 1. And luckily we get to write this in factored form. So what factor should I put for the hole at 3? X minus 3. Where else should an x minus 3 go? Because our rule is that those should cancel out. That's going to create a hole at 3. Okay, we've got a vertical asymptote at 1. What should I put and where should I put it? And I wish that was all there was to it. There's a little bit more we need to think about. Yeah, we need to figure out this part, okay? Because if you were to put this in the calculator, there would not be a hole at 3.5. There would be a hole at like 3.5. Just take my word for it, I did it this morning just out of curiosity. So we need to figure out something, okay? I want you to take your pencil and I want you to just pretend those are gone. Pretend those have already canceled out. Let's plug in 3, which the only place to plug it in is down here. What is 3 take away 1? 2. I'm needing the situation. Remember what you learned up here? Oh, that's super easy. Just cancel these out. Plug in the value of the hole. So up here we plugged in 2, and that's how we got our negative 6 over negative 1. Think backwards then. I need to figure out something that when divided by 2, where am I getting the 2 again? 3 take away 1. I'm plugging in the value of the hole. 3 take away 1 is 2. What divided by 2 would give me a hole at the y value of 5? 10. I'm going to say all of that again because I know for some of you, like, what in the world is happening? Okay, take this whole thing as a proof. And let's say you're just totally trusting the teacher that 10 goes there and you have no idea why. Here's why. Okay, if the x minus 3 is canceled, then where I could find the location of this hole is I would plug in the value of 3 where I know the hole is. That's 3 take away 1 is 2. 10 divided by 2 is 5. So that's why there's a hole at the ordered pair 3, 5. We're just having to think backwards and we're having to make that happen. Yes. Is technically a factor. It's just not a factor that will give you So you can see why I saved this for the end. It's a little abstract. Let's try it again. We only have one more example to kind of understand what's going on. This one's going to make try it. Instead of a 10, we could have this, which would mean I'm plugging in a 3. That'd be 10. Yes, that would work. Now that's going to drive some of your classmates crazy because what that means is there's more than one don't have both of them there, you can choose. So I really, really like that. Maybe you prefer that, you guys. If the 10 just didn't really work for your brain, you can have an x plus 7 up there instead. Because when you plug into that, you're still going to get 10. Really good insight there. That would mean, if we do it that way, that would mean that the graph crosses the x-axis at negative 7. Because these on top give you the zeros. Just as a little aside there. Bringing in some old knowledge. All right. I'm hoping all of you can look at this and you can say, all right, there's a hole at 2, 4. The hardest part is going to be creating a situation where the y value is 4 when they're plugging a 2. And there is a vertical asymptote at, oh, I did that wrong. I've done this problem 3 times, and every single time I don't see the negative 2, the little tiny, teeny little negative. So there's a hole at negative 2, 4. Okay, I apologize. Negative 2. And there is a vertical asymptote at negative 1. Teeny tiny little symbols matter. All right, so get your fraction bar set up. Oops. We know there's a hole at negative 2. Oops. So x plus 2, x plus 2. We know there's a vertical asymptote at negative 1. Be careful with those negatives. I mean, even I just accidentally put minus 2, so just watch your symbols. This one? Yeah, because the vertical asymptote is at positive. Over here it's at negative. Okay. This is going to make sense to some of you, and for some of you it's not, and that's okay. You have to have a squared on this one because of this. Think of sign charts, and what I'm going to need to make sure would happen in a sign chart situation is that everything stays positive. In math, if we want everything to stay positive, we can just stick a little squared symbol on it. So no matter what I plug in, the value is going to stay positive. How do I know it needs to be positive? Because it says that the y values are always going to be approaching the positive. Now let's deal with the 4 thing. 4. As of right now, if I cancel those out, and I plug in that negative 2, where I know I have a hole, that's negative 2 plus 1. What's negative 2 plus 1? Negative 1. And what's negative 1 squared? 1. What divided by 1 will give me 4? You could have a 4 on top. You could have a 4 on top. What else could you have on top? Give me another option. You could have an x plus 6 on top instead if you wanted to. I hope you're hearing me. These would both not be there. It'd be one or the other, the purple or the pencil, because negative 2 plus 6 would give you 4 on top. Anybody think of another one? So they're just trying to create this 4 by plugging in a negative 2 for x. Negative 2 plus what would give me 4? Negative 2 plus 6 would give me 4. How could you do it? Ooh, creative. That would give me negative 2, or give me 2, because negative 2 plus 4 is 2, and 2 squared is 4. So any of these things would work. There are lots of options. I'm just going to keep it as simple, or in my opinion, this is the most simple one. I'm just going to put a 4. Now, I hope that this information helps bring down your anxiety. You're not going to have anything this intense on the test next week, where you have to just take limit statements in. If you do, it's not going to involve this extra component of figuring out, like, there's a tool and that's on top. It's a very gentle problem that's on the test on the previous one. So that's where we're going to end the notes.